Hi everyone. Well, let's see if this works. What I'd like to do is talk to you a little bit about inferential statistics. So far, everything we've done has to do with descriptive statistics. So the things we've covered over the last few weeks relating to how to define or how to describe different kinds of nominal and ordinal data, and how to describe different kinds of interval or ratio data, crosstabs, those are all examples of descriptive statistics. Today we want to talk about inferential statistics, and in the process of doing so, these four topics are what we would like to attempt to cover. So I'm going to start with a first video in which we discuss the characteristics of the normal curve, and then we'll have a couple other videos where I'll talk about application of the normal curve, confidence interval computations, and then we'll end with the hypothesis testing steps. So let's start with the normal curve, and in the process of doing so we will start by describing or defining what inferential statistics is. So let's get to that. Herein lies our definition, and let me show everything on this slide. So any procedure statistically that we use in which we select from a sample so that we could draw conclusions about the population. So the example here is perhaps we want to know something about students at University of Arizona, or maybe it's HISD elementary school administrators. Whatever that population is, we probably won't have access to every single person. So normally what we do is we select a sample from those populations using the ways in which we talked about in 7603, and I'm just reminding you of what those are. You could pick from a hat. In this case, you would write everybody's name down, put on a piece of paper and put in a hat, and then you select however many from the hat that you want for your sample. That's not a practical way of doing it, but that principle is what undergirds what random sample selection is all about. The two ways in which we've actually done sample selection is through the table of random numbers. You might want to go back to 7603 and do a quick review of how we use the table of random numbers to select samples. And finally, I gave you a formula in Excel that you can use to generate random samples. So the bottom line is that one of the things we attempt to do is select a sample from a population. We test that sample, and it's the information from that sample that we infers the entire population has those similar characteristics as well. So why are we sure that we could select from a sample and make assumptions about what the entire population is like? It's because of something that we know about the normal curve. I'm sure you've seen the normal curve before. It's that bell-shaped curve. I'll show you what it looks like in a second. The normal curve is this distribution of scores with this bell shape and helps us to determine the probability of any individual score occurring. Let's give you three very quick examples of how this works. So imagine we created a pie chart in which we have collected information about children, more specifically different kinds of after-school care that children receive. And let's say we had a huge population from which we selected this information, and we crunched the numbers, and this is what the after-school childcare looks like in terms of percentage of students who participate in these ways in which they are taken care of. Given what we know of the entire population of after-school care, we could select any individual child and ask questions like, what's the probability of, if I find a child, what's the probability that that child got center care? Well, based on this data, one would say 15%. Or we might ask, what's the probability of that child receiving care from the home? Well, home care is about 33%, so we would assume that there's a 33% chance that that child receives care from the home. We could illustrate this same data using bar graphs. Ask the same questions, you'll end up with the same answers. Or, which is what we most often do, is we could use a histogram to determine probabilities. Now, if you recall, the difference between a histogram and a bar graph are two differences. With a histogram, the bars touch, and also with a histogram, the range of scores on the x-axis are from lowest to highest or highest to lowest. So we don't use group data to develop histogram. We use interval or ratio data for histograms. All right. Imagine we had a population of 150 students, and from those 150 students who took the Miller analogy test, and their scores ranged from about 30 to 100. So we built this histogram showing the range of scores. In the same way that we used a pie chart or bar graph to determine probability, we could do the same here. In this case, we could say something like, we could ask how likely is it that we would find someone who scored 50 on the Miller analogy test. Well, we would go to the block that has 50. So if you notice the cursor where we have 50, and you'll notice that 10 of the 150 students scored 50. So the probability is 10 out of that 150 times 100 to get a percentage would be about 6.67%. So we would conclude that if you were to find someone out there who took the MAT, if you were to ask what's the probability of them getting a score of 50, that probability would be 6.67%. So essentially, we can use the normal curve, which a normal curve really is just a histogram with a large number of subjects. We could use that same principle as we look at the normal curve. So let's look at what some characteristics of the normal curve are. Let me show all of these to you at once. Again, we said the normal curve is a bell-shaped curve that has certain characteristics, right? Three main characteristics are that the mean, the mode, and the median are all the same and occur at the peak of the curve. If you look at the cursor, you'll notice where the peak of the curve is, and so that's where the mean, the mode, and the median are. Now, if you reflect back on some of the data that we've analyzed up to this point, we have found that in most instances, the mean, the median, and the mode are pretty close to each other, but they were not identical. But in this case, we are saying that the true characteristics of a normal curve are where the mean, the mode, and the median are exactly at the peak of the curve. The second thing we could say is that if you draw a line from the peak of that curve to the x-axis, that everything that falls on the left of that curve would be 50% of all the population of scores, and 50% would fall on the right-hand side. The last point we want to make about the normal curve is that we generally assume that you could take any variable you could think of, and if you were to plot all the scores from that population, that they would fall into an approximately normal curve, something that looks like this. Okay, so why is that important? That's important for the next thing we want to do. How do we predict probabilities based on features of the normal curve? And so that is the next video clip that I am going to prepare for you.